Hello, my name is Björn Tackmann and I'm a cryptography researcher at Dfinity. On our path toward Mercury, I have led the research on topics related to identity and authentication. Let me explain what I mean by identity and authentication and why we do things differently on the internet computer than on the traditional web. When you log into a website today, you're likely asked for a username and password. Your username, nowadays most often your email address, serves as your identity, the unique identifier that connects all the data on the servers to you. Your password is the means of authentication. It turns out that passwords, despite their wide use, are actually not a good mechanism for remote authentication. If you follow IT news, you've certainly seen lots of headlines about attackers extracting the password databases from company A or service provider B. But even when industry best practices are followed, such as only storing a so-called salted hash of the password, recovering passwords from such a user database is only a matter of computational and thus monetary resources that an attacker is willing to invest. The internet computer is designed to provide security against malicious behavior of individual compute providers by replicating data and computation across multiple data centers. Replication, while protecting the integrity of the data, does not protect against leakage of information, and thus the use of passwords on the internet computer would still be subject to the same security issues as on the traditional web. Thus, we replace passwords by proper cryptographic authentication. The main cryptographic mechanisms we use for authentication on the internet computer is a digital signature scheme. Digital signatures are a pretty standard concept. They are generally thought of as consisting of three algorithms. The first one is key generation, which you can think of as an analog for choosing a password. Key generation creates a pair of keys, a private key that has to be kept secret, just like a password, and a public key that is derived from the private key but can be made public. The second algorithm is signing. It takes a message and the private key and produces a signature. When we use digital signatures for user authentication, this algorithm is run on the user side where the private key is held. The third algorithm is verification. It takes the message, the signature and the public key and verifies whether the signature matches the message and public key. The crucial property here is that unlike when checking a password, which requires the secret password in the clear on the server, the verification of a signature can be performed merely on public information. The server stores a list of public keys, one for each user, and neither the public key nor the signature have to remain secret. Web authentication is a recent standard of the World Wide Web Consortium and mainly targets two-factor authentication for web applications. Second-factor authentication means that besides the password, logging in to a web application also requires an additional security factor, usually a secure device that the user owns. In practice, that could be a secure USB key or a secure chip that is built into the user's end device and activated via biometrics. The secure chip stores cryptographic keys. As the cryptographic keys never leave the secure chip, they remain secure even if the user's computer or phone is infected with malware. When web authentication is used as a second factor in a web application, the protocol flow is as follows. After the user initiated the login process by providing username and password, the web server will generate a random challenge and send it to the user's browser. The browser then sends the challenge to the secure device, which requires user interaction before it signs the challenge. The signed challenge is then sent back to the server, which verifies the signature on the challenge relative to the user's registered public key. This ensures that logging into the web application requires holding the secure device in addition to the password. We build on the fact that web authentication is an open standard that uses digital signatures for authentication and is already supported on a broad range of devices. When adapting it for the internet computer, though, we had to overcome a few hurdles. Web authentication assumes the session-oriented client-server model of the traditional web, where a user authenticates once when logging in with the application and sends subsequent messages within the same session. The Internet computer, by contrast, implements a model where each request is authenticated individually. In particular, there is no server that can generate a challenge to be signed by the secure device, as there is no stateful session between the browser and the Internet computer. Recall, however, that in the typical web authentication flow, the secure device provides a digital signature on the challenge sent by the server. To implement request authentication using the same protocol, we simply use the request itself as the challenge and have it signed by the secure device, analogous to our general request authentication scheme. While web authentication is great for storing keys securely, it binds those keys not only to the device, but also to the particular canister. The reason for this is the browser security model, which strictly separates the state accessible to different applications running in the same web browser by their so-called origin. On the web, you can think of an origin as roughly corresponding to one website. On the Internet computer, each origin corresponds to one canister. This strict state separation is vital for security, but it also makes functions such as key backup or support for accessing the same canisters seamlessly from multiple devices tedious, since all those operations have to be performed separately for each canister. We resolve this issue by using the identity provider, which is similar to the sign in with big tech functionality that you certainly know from the web. When a user first loads the front end of a given canister, that front end can present a sign in with the IC button. When the user clicks that button, the browser is redirected to the Internet computer identity provider, a specific application that allows the user to manage their keys and identities. In the identity provider, the user can then decide whether to allow the canister front end to use the identity. If the user approves, the browser is redirected to the canister front end and can access the canister under the user's identity. The identity provider mechanism again uses the session key and delegation mechanisms. The canister front end generates a session key pair and transfers the public key to the identity provider with the redirection. The identity provider, if the user confirms, generates a delegation and returns it to the canister front end. As an additional benefit over sign in with big tech, the complete authentication flow in the identity provider happens on the user side, so there is much less exposure of private user actions and thus much less tracking. The mechanisms are described in detail in the Internet Computer Interface specification that we released recently, and we're looking forward to seeing what else our developer community is going to build from it. Thank you for your attention, and I wish you a lot of fun building on the Internet computer.